Heavenly Father, we thank you for this day again. I thank you for this class, these students. Just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So here's the example. I started to try. Well, I wrote on the board, but we didn't get to it yesterday, obviously. So how do we do this integral? I mean, obviously you don't want to just do it. Yeah.
I was thinking maybe like
You think cylindrical coordinates? I agree. I think probably the first thing to do is to try to process the bounds. What do they mean, right? So like the z bound shows us we've got 0 less than or equal to z less than or equal to 9 minus x squared minus y squared, right? Now, one thing we should notice, like right off the bat here, is that we could also write that as 9 minus r squared, right? So I think you're right. I think cylindrical coordinates are probably helpful, and it's easy to translate this into its cylindrical equivalent like that, for one thing. Let's see here. We also have 0 less than or equal to y less than or equal to the square root of 9 minus x squared from my y bound, right? And let's look at equality here. That gives us y squared equals to 9 minus x squared, which of course is actually x squared plus y squared equals to 9, right? So if I plot that in the x and the y, right, we've got 0 below y, and then this thing, so we're in this kind of region here, right? That's how I could understand that. And then of course, well, the x bounds, they can already see that. That's kind of here, right? 3 and minus 3 for the x. So let's see here. If I try to plot this region three-dimensionally, I mean, I guess you don't really need to necessarily, but if I was to foolishly attempt that, it's something like the x goes from minus 3 to 3, right? So it's some kind of like, here's what it looks like. Here's the base of the region, right? The highest point on it is achieved when we put x and y both 0, in which case we get z equals to 9, right? So it's some kind of, like this kind of deal here. And do you have to draw the picture accurately? Not really, right? Because we can set this up now. This is actually going to be equal to the integral. Let's see here. In terms of cylindrical coordinates, we've got what? We're sweeping from what? Here, theta equals to 0, over to here, theta equals to pi, right? So we've got 0 less than or equal to theta less than or equal to pi. And my r, I believe, is going to go from 0 to 3. So we can, whichever one of those we want to do, I'll do the theta last, 0 to pi. I'm going to do my r from 0 to 3. My z bound is most exciting, 0 to 9 minus r squared, right? And, okay, well now we've got to face the music here. What's this? What's the integrand? It's r, right? So I get r squared dz dr d theta. And the reason for this is we had dv equals r dz dr d theta, right? And so this r and this r together give me the r squared, right? And now we do the integral, right? So like, what do I got? I got the integral from 0 to pi, the integral from 0 to 3. The dz simply integrates to r squared times 9 minus r squared. all right? And so I've got integral from 0 to pi d theta times the integral from 0 to 3 of, looks like 9r squared minus r to the power 4 dr, which is going to give me pi times, well, 9 times 3 cubed divided by 3 minus 3 to the power 5 over 5, which is like pi times, I think, 81 minus, 243 over 5. Which is 405 minus 243 over 5, I think. What's that? 162? Yeah. Whew, good. That's what I had in the notes before I deleted this example. But in the example, my original picture, I had gotten the bounds were right, but one of my pictures was wrong. So that's why I deleted the picture. So, anyway. So there you go. This is a pretty common kind of example. Do you guys have any questions? No? All right. Well, I do have more examples. One I wanted to show you guys is calculating the moment of inertia of a sphere. Sphere with uniformly distributed mass m, all right, and radius r. And we're going to find the moment of inertia about the z-axis, all right? So this is basically the idea is to think about the sphere, all right, spinning around the z-axis and the little bit of inertia that a little bit of mass would have. So you think about a little bit of mass here, all right, and you're thinking about it spinning around the z-axis like that. Well, the distance from the axis to the little bit of mass is the radius, right? The cylindrical radius, and so the little bit of inertia that it gets is r squared dm, because that's how we calculate moment of inertia in physics, right? But then to find the total moment of inertia, we have to add this up over the whole sphere, and so the moment of inertia for the sphere, and this is about the z-axis, is going to be equal to the integral over the sphere. Let me call this the ball of radius r, over the ball of radius r of r squared dm. Right? So that's the integral we have to do. Now dm, let me be, how do we understand that? Well, this is a uniform mass density, right? So we know that dm dv, right? The mass per unit volume, if it's uniform, it's equal to the total mass divided by the total volume. What's the total volume? Well, we worked that out the other day, right? The volume of a sphere is 4/3 pi r cubed, right? And so that's my, that's the mdv, which means that I can rewrite this dm simply as the integral over the ball of radius r of r squared times, let's see here, m divided by 4/3 pi r cubed, all right, times dv. Now that's just a number. So, let's give that a name so we don't have to keep writing it throughout the calculation, right? In my notes, I've been calling this the density. I've been calling this quantity delta. It's just a constant, all right? And so this is equal to the integral. We can pull the delta out front, is my point. Delta times the integral from 0 to 2 pi, integral from 0 to pi, integral from 0 to r, right? And let's think about this. So r is what? In terms of spherical coordinates, we talked about this. R is rho sine phi, right? That's what r is. Now dv in spherical coordinates, remember, is rho squared sine phi d rho d phi d theta. And so put those two things together, we got ourselves a rho cubed sine squared phi oh yeah, d rho d phi d theta. Now this is very pleasant because there's no, all of the bounds are rectangular, they're constant bounds, so we can just multiply the integrals, right? So this is like equal to the integral of delta times the integral from 0 to 2 pi of d theta. That's easy enough to do. The integral from 0 to pi of sine squared phi d phi. And then the integral from 0 to r of rho to the power 3 d rho. Did I make a mistake?
Isn't r just, this is p sine, but it's r squared. So it would be
Oh, yes, thank you. Oh, thank you. So my r squared, it was rho squared sine squared. Well, now I'm going to actually have to think about this integral. Rats. Integral of sine squared from 0 to pi is just, like pi. But, let's see here, I think. I could be wrong about it. Maybe it's pi over 2. Pi over 2. Yeah, so that's a sine cubed, thank you. And that gets us an additional power of rho. So we got rho to the power 4 sine cubed. There we go. Fixed, right? All right. So some of these things we can do without much effort, like the theta integrals. So we got a delta, we got a 2 pi, we've got a r to the power 5 over 5. That's easy, right? Now the integral from 0 to pi, that's of 1 minus cosine squared phi times sine phi d phi, right? That's how we deal with integral sine cubed. And so that gives me I make a u equals cosine phi substitution, so du is minus sine phi d phi, and my u of 0 is 1, my u of pi is minus 1. So put that into practice, and we got delta times 2 pi times r to the power 5 over 5, integral from 1 to minus 1 of 1 minus u squared times minus du. I don't like to write down there. Sorry guys, I'm going to do a kind of weird, poor planning on my part. I should have started further up on the board, right? So I'm going to do this. Equals. So we've got 2 pi delta r to the power 5 divided by 5, right? And this here that's an even function, so I'm going to replace that with the integral from 0 to 1 of 1 minus u squared. Now let me explain my logic here. I flipped the bounds to absorb that minus. And then I'm going from 0 to 1 rather than from minus 1 to 1 because this is an even function. So to be fair, I still have to do what? I still have to multiply by 2. So I'm going to trade that 2 in the front for a 4. Now you can just do the integral. It's all the same. But what we got then is a 4 pi delta over 5 times r to the power 5, right? Times, let's see here, 1 minus 1/3, I believe. All right, so we've got 4 pi r to the power 5 over 5. This is 2/3. And my delta was what? It was m divided by 4/3 pi r cubed. So what do we got here? 4 pi's, they be canceling. This 3's canceling. What are the winners in this game here? Yeah, r squared remains. So like this 2 survives, the 5 survives, but the 4 pi, this 4 pi cancels that 4 pi, and this 3 cancels that 3. And we're left with 2/5 m r squared. That is the moment of inertia that you need in physics 230. Yeah.
Just a quick question. Why are the bounds down there -1 and 1, but up top it's 1 and 0?
Because I doubled it. I traded that 2 for a 4, and I flipped the bounds to absorb the minus, and then it's an even function. Even function integrated about a symmetric interval of the origin is the same as twice the integral about just the positive integral from the origin. Yeah.
When the function's odd, you change the bounds to?
If we're integrating an odd function about a symmetric interval of the origin, the answer is just 0.
What is that odd function again? Can you just
An odd function is a function, by definition, f of x is odd. Even. F of minus x is equal to f of x. Odd. F of minus x is equal to minus f of x. Any other questions? No? All right. Let's see here if I can find a good example for us.
Could you do an example about volume bounded between or bounded by a curve?
Volume bounded by a curve? I don't know.
Whatever. Like
Just like a bounded volume? Sure, I think I got some of those. Let's see here. This is physics. So physics says that the moment of inertia of a little point mass rotating a distance r from the axis of rotation is r squared times the mass. And so I'm thinking of this as a solid ball. It's all revolving. It's a rigid body. So that's add up the moment of inertia for each little bit gives us the total moment of inertia. So it's physics. Yeah.
So we had a question for this on the test. Could you give us, like,
Do I expect you to know physics? No. I would remind you that, this is, calculate the moment of inertia about, the z-axis, and I probably would I probably would give you the formula to get started at least. I might not tell you, I might write the formula like this so that you have to think through it, but all right. So you guys wanted something bounded by, you said a plane?
Or just a volume bounded by...
Surface, like something where there are bounds and we have to work it out?
Yeah.
All right. Like a cylinder or something. Okay, so example 3. I don't know, how about we have this plane, x plus y plus z equals to 4, right? And maybe I've got a plane down here. Maybe I've got a, let's see here. I don't know, making up examples is the hardest part. Well, we can do the boring thing. We can just find the volume bounded between this and the, coordinate planes, for instance. Right? So, like this, find volume bounded by plane and the coordinate planes. All right, so we can make pretty quick work of this problem at this point, I hope. This is kind of the most interesting part right here. That is where z is equal to 0, which means x plus y is equal to 4. So if I graph that just on its lonesome x and y like this, we've got, it goes from 2, and this is also 2, right? Oh, wait a minute, no, duh. What is that? I think that's 4, and that's 4, right? Yeah? So basically, we're going from here, this is 0 for x, this is 4 for x, this is 0 for y, this is 4 for y, despite my picture. And I guess this is also 0, 0, 4. Everything's 4 here. I'm sorry, this is not, I should have made the numbers different so we could see some contrast here, but it's too late. So the volume then, I do integral from 0 to 4. Sorry, let me do integral of dv over this region, right? We call this whole thing T for tetrahedron. So I can integrate from 0 to 4. And, okay, I got to be, what's here? 0 in the bottom, and up here, what's this equation? Y equals to what? 4 minus x, right? So I can integrate from 0 to 4 minus x here. Then for the z, I go from 0 up to 4 minus x minus y, right? I've got dz, then dy, and then dx. I think this is your question, right? One like this, but we'll try to do another after this. This one's we've kind of done this one before, right? But it's good to do it again. Some of you were more lost last time we did it. Hopefully less of you are lost on this at this point. right? All right, now I'm integrating with respect to y. I get 4 minus x times y minus 1/2 y squared, evaluated from 0 to 4 minus x. Something kind of cool happens here. If you think about it, we get, like, let's think through this. We get 4 minus x squared, right? Minus 1/2 of 4 minus x squared. Now there's a smart way and there's a dumb way to go forward here. The dumb way is to multiply it all out, right? And then forget to distribute the minus and get it wrong because of carelessness, something like that, right? But here, notice that it's the same thing. So I'm just subtracting 1/2 of it. So what I'm really up against here is the integral from 0 to 4 of 1/2 of 4 minus x quantity squared dx, right? And there are various ways to go forward here. Like, yes, we could distribute that. Let me just do that. You can make a substitution here, do that integral if you wanted, but I won't. Integral from 0 to 4 of 1/2 of 16 minus 8x plus x squared dx, which is the integral from 0 to 4 of 8 minus 4x plus 1/2 x squared. I probably should have just kept that half out front if I was smarter, but it's too late. So that's 8 times 4 minus 4 times 4 squared, which is 16 over 2, plus 1/2 of, not 1/2, it's 1/6, right? Because the third times 2 is 6. So integrate x squared to x cubed over 3, 1/6, and then I've got 4 to the power 3 there. I'm going to start over here. So that's equal to 32 minus 32. So plus 64 divided by 6. So the answer is what? 32 over 3? There you go. That's the volume of this tetrahedron. Okay. Let me do a higher dimensional integral for a change. We haven't done many of those, you know. So I won't try to draw a picture. I'll describe it with inequalities. So here, example 4. Consider, let's say, E equal to x, y, z, u, v, w, such that x squared plus y squared plus z squared is less than or equal to 4. And on the other hand, thrice. Twice or thrice? Let's say thrice. X squared plus y squared I'm trying to find the words to say this here. think I need to write 0. No, still wrong. The square root of 3 times x squared plus y squared is, still got it wrong. 0 less than or equal to z less than or equal to the square root of 3 times x squared plus y squared. There, I got it. Okay, great. That was what I was after. And let's see here. I also have that let's say u squared plus v squared is less than or equal to 9, and u plus v plus 4 is less than or equal to w is less than or equal to, I'm sorry, I should have said like minus 4 here, and here 8. All right. So let's calculate the integral. I don't usually do 6 integral signs, but there we go. But we'll just calculate the hypervolume of this. I won't even slap an integrand on there. All right. Maybe I should, though. Maybe I should. No, I won't. So we can use notation d6th, d6v, right? So in this situation, you see, there's no, you notice that there's no interplay here between the x and the y and the z and the u and the v and the w, right? So what that means is we can look at this actually as the product of 2 triple integrals, right? Yeah. So this is just a way for me doing 2 complicated examples at once in the interest of confusing the students more. Mission accomplished, I guess. Okay, so integral over, let me just give this part of the conditions a name. Let me call this Pac-Man. So over those conditions, dx, dy, dz, right? Times the integral over ghost. And I'm going to call all this stuff over here ghost. But that's, of course, du, dv, dw. Okay, so now we just got a product of triple integrals, which maybe, do we know how to do those? Well, like what is Pac-Man if we just think about x, y, z space? We've got what? We've got 0 less than or equal to rho less than or equal to 2. That's this, right? That says the spherical radius is between 0 and 2. Now the other one is a little bit tricky, right? This right here. Well, let me write it out. So that the equality we've got. What do we got? We got rho cosine phi, right, is equal to the square root of 3. X squared plus y squared in spherical coordinates is rho squared sine squared phi. Thanks for that. You guys told me about the square just a second ago, right? So that's actually rho cosine phi is root 3 rho sine phi. All right, great. So apparently tangent phi is 1 over root 3. what I'm trying to say is the second condition here, we can recognize what that is. It's a cone. It's a cone of a particular angle. It's a cone of angle inverse tangent of 1 over root 3, which is what? Pi over 6, right? And so if we look at, Pac-Man, we can describe it by this right here. And of course, what can you say about theta? There's no restriction whatsoever, right? Now, I could have messed with the theta if I tacked on another condition like x is positive, right? If I'd said x is positive, that would have forced us to do like pi over 2 to minus pi over 2. If I'd said y is positive, we would have had to go from 0 to pi, right? But at the moment, we don't have those, so we're just, here it is. We got integral from 0 to 2 pi, integral from 0 to pi over 6, integral from 0 to 2 of rho squared sine phi d rho d phi d theta. That's the Pac-Man integral, right? And then I need to multiply that by what? What about Ghost over here? What's going on? Now this one is quite clearly not a spherical problem, right? So we need to invent coordinates over there that suit the problem. What coordinates should we invent? How about this? We should let, r equal to, let us say, I'm not r, what's wrong with me? Good night. U is equal to, let me use an s cosine beta. V is equal to s sine beta. And w equals to w, all right? If I do that, then the Jacobian of UVW with respect to S beta W, it's just equal to S, because this is exactly analogous to the regular cylindrical coordinates. I'm just using S for the cylindrical radius rather than R, because I already used up R. Well, anyway, I'm just trying to use a different notation to, I guess confuse the students. So mission accomplished, maybe. Okay, so the first equality up here is s squared less than or equal to 9, right? So really we could say 0 less than or equal to s less than or equal to 3. That's how the cylindrical radius implicit within the Ghost conditions is playing out. And the W, this one's a little bit more exciting, isn't it? That says, S cosine beta plus S sine beta minus 4 less than or equal to W less than or equal to 8. And I guess, so once again, the angle that sweeps from 0 to 2 pi, right? There's nothing stopping it. So like this, if you want me to picture this in UV space, we're talking about something like the top of it is at 8, right? And then there's a cylinder, right? And then down here somewhere, there's this, U plus V minus 4 equals to W. All right, I'm not sure exactly where everything is, but this is kind of a crude picture of what's going on here, okay? Again, because XYZ has no bearing on it, so we can analyze the UVW part separate from the XY part. And so we have integral from 0 to 2 pi, integral from 0 to 3, the exciting bounds, integral from S cos beta plus S sine beta minus 4 to 8 of what? The Jacobian was S, so it's, as usual, S. We've got dW, ds, d beta.
How did we find that Jacobian?
By analogy. I mean, if you want, I can write it out. but it's because this is the determinant of, you know, US, VS, WS, U beta, V beta, W beta, UW, VW, WW.
Did we define our U and V intentionally so that our Jacobian would become, or did we?
I'm introducing non-standard cylindrical coordinates on the UVW space. I mean, these are cylindrical coordinates on UVW space.
Okay.
I mean, you could use r and theta there, but then I'm in danger of confusing students because r is equal to the square root of x squared plus y squared, and x is equal to r cosine theta, y is equal to r sine theta. That notation is kind of reserved in here, right? In some of your minds, it's reserved. If I write r, you automatically are saying it's square root of x squared plus y squared, right? So I can't say r is equal to, you know, r squared is u squared plus v squared, because r squared is x squared plus y squared. So I need to invent a new letter. And so I just invented s to replace r and beta to replace theta. But they're playing the same role, which is why we knew that worked out to s, because this works out to like, this is 0, these are 0, this ends up being 1, and this ends up working out to s
Oh, okay. So
times
all
cosine.
cylindrical coordinates, we're just using different
Mm-hmm.
letters to represent.
Right. I'm not going to work this out because we worked this out before. You guys know what to do from here. All right. Other questions? Another example with what?
Wedge products?
Wedge products. Oh, sure. Sure. Well, he asked if it could be on the test, so I said, yeah, it could be on the test.
No, I mean, can you explain the wedge product?
Yeah, we can look at an example. Sure. All right, so let's come up with a I mean, is it a big part of the test? Well, no, obviously not. Example 5, so like, let's see here, coordinate change. Let's say x is equal to, I don't know, need to come up with a letter here. Let's say t cosh phi, and y is equal to t sinh phi, right? So this is we'll just, let me do a two-dimensional example, at least to start with. Then if I was to calculate dx wedge dy, I could do that. So let's see here. I'd have what? I'd have, you know, cosh phi dt plus t times the sinh of phi d phi, right? Wedged with sinh phi dt plus t cosh phi d phi. All right, so that gives me, I'll write it all out. Cosh phi sinh phi dt wedge dt plus cosh phi times t sinh phi dt wedge d phi plus t sinh phi d phi wedge dt plus t squared sinh phi cos phi d phi wedge d phi. All right. So first of all, what I did is just kind of silly. I just distributed, right? Yeah.
How does the wedge work with, like, what are its properties with, like, distribution and stuff?
It distributes like normal. We can pull numbers out. The only main thing that's different is that the wedge product of differential with itself is 0 and they anti-commute. So like, this is by definition 0, and likewise this is by definition 0, but this right here we can rewrite as minus dt wedge d phi. That's again by the basic defining properties of the wedge product is anti-symmetric. Okay, so then that gives me, as it happens, 2t cosh phi sinh phi times, well, oh, wait a minute. Did I distribute wrong? Oh, just a, yeah, maybe, just a second. Let me, t.
Second one should be 2 cosh. Not cosh.
Somewhere I should have 2 coshes. Yeah, which one?
The second term, instead of cosh, it should be cosh squared.
Cosh.
It says cosh sinh, but it should be.
Oh, this should be cosh. This right here, that's the offending one. So, yes. Sorry, I'm too close to the board apparently. That should be cosh. Because that was from this times this, which gave me this dt and this d phi. All right, so we don't get, oh, okay, well that's better. So apparently we get t times cosh squared phi minus sinh squared. Oh, that's kind of cool. It's cosh squared minus sinh squared phi dt wedge d phi, right? In other words, we get t dt wedge d phi. Now, of course, that's not the standard. I mean, this implies, from this I can cipher, this means that the Jacobian of xy taken with respect to t and phi here is equal to t.
How did we get that minus?
That minus comes from flippy-flopping these,
Oh, right.
because I had dt wedge d phi there rather than d phi wedge dt. So we can count, yeah,
Also, one more question, sorry about the
It's okay.
distribution. When you distribute, how did the term, like the variables, like t cosh go in front and be multiplied by the other cosh, and then the dt is wedged with the d? I'm already looking myself.
so it's just the usual law of distribution, like FOIL if you like. I do this times that, and I pull the sign out, cinch out front. Whatever the coefficient is here, I just move to the front. So like, here, let me just, if I have a dx plus b dy wedged with c dz plus d dw, the way that works out is a times c dx wedge dz plus a times d dx wedge dw plus b times c dy wedge dz plus b times d dy wedge dw. It's just the usual standard distribution laws, and you can pull scalars out. The difference, of course, is that the wedge product is anti-commutative. So like if I also have that, like, dx wedge dz is minus dz wedge dx and such, all right? But anyway, I'm trying not to get into that too much at the moment because it's not really relevant to what we're currently doing. I will say more about that at the end of the course, but we're not there yet. So this is the determinant. So I just want to show you we can calculate the same thing using the Jacobian, determinant. And so let's see here that we've got cosh phi, sinh phi, t sinh, t cosh, and of course we get t cosh squared phi minus sinh squared phi, right? So no surprises. The previous method of calculation still works, right? Still works. But you can use the wedge product to calculate determinants if you want. Yeah.
What would t
T equals 1 look like in this coordinate system?
What would t equals 1 look like in this coordinate system?
Because x equals 1 is a line, r equals 1 is a circle.
Well, yeah, I mean, t equals 1 is a hyperbola, yeah. It's the unit hyperbola. It's x squared minus y squared equals to 1. But since x is equal to cosh phi, that means that x is positive. So it's actually the right branch of the unit hyperbola, I think. These are hyperbolic coordinates, but yeah. Interesting.
You also use like, I guess it's can you use those in integrals as well? Like,
Can we
when would be advantageous to use volume?
I mean, there must be problems where it's helpful, but I don't have examples in my notes of that. So, I can try to come up with some. Let's see here. So, like, let me just say, since you guys are asking me, let me just say a word more about the wedge product in terms of like what it has to do. Yeah.
What would be like a scenario where we'd want to use wedge rather than just Jacobian?
Oh, the one I showed you last class, where we're calculating like, you know, something big, right? So like, I mean, here, let me show you one that's like that. Example 6. I mean, in some sense, I was using it in my example that I just erased in the following sense. Suppose I have, you know, x1 is rho cosine theta sine phi, right? And x2 is rho sine theta sine phi, right? And x3 is rho cosine phi, right? And x4 is, I don't know, rho cosh phi, cosh psi. And x5 is rho sinh psi. This is a particular coordinate transformation on R5. What's its Jacobian? See, that's horrible to calculate. Oopsie, I need to introduce something else here. I can't just use rho. I need to use something else. Like, let us say rho, I'll put a t here, t rho. So, you know, rho, theta, phi, t psi. To calculate that Jacobian, I'd have to work out a 5 by 5 matrix and calculate the determinant of it. We could do that, but it's also true, like this is the general theorem, that dx wedge d2, dx wedge d3, wedge dx4, wedge dx5 is going to be equal to this thing. Let me just call this J. J times, excuse me, d rho wedge d phi wedge d theta wedge dt wedge d phi d psi. I meant to put these in their proper order. I'm sorry. My bad. Right. With the wedge product, I can simply I can use what I already know to simplify parts of it. Like, all I'm doing is spherical coordinates here, right? So this, we already know what happens there. That works out to rho squared sine phi d rho wedge d phi wedge d theta, right? We worked that out yesterday, actually. Yesterday, I showed you how to work that out using polar coordinates as a backdrop. So we didn't actually have to do the 3x3 determinant calculation. We just kind of repeated. Look at what I did yesterday. It's there. But now here, I think this one's going to be unpleasant because I just made it unpleasant. But we have the differential of, you know, t rho cosh v, it's cosh psi. Oh, this is unpleasant. Wedge, the differential of t rho sinh psi, right? And I can just focus my attention here on this calculation, right? So this is going to be, you know, like t cosh v cosh psi plus t sine sinh. Did I say sine? I meant sinh psi d rho. I'm just putting the d rho terms first, and then I've got, you know, t cosh psi t cosh psi dt. Good grief, rho cosh psi dt plus t rho sinh psi d psi. Oh, phooey. Sorry. I've got to, so it's this. And then, like, if I'm smart about this, I can just drop. See these terms? They don't matter because there's a row over here, and so like the wedge product is it's associative. Well, it's not it is associative, but the point is I can commute with the minus. You know, I can move the d rho over here, and eventually I'll get to d rho wedge d rho, which is equal to 0. 0 wedged with anything is 0. So like these terms I can just drop. And I just have to take the wedge product of this and that, right? And that we already just did over here, right? Because if you pull the rho out, we have rho squared sine phi d rho wedge d phi wedge d theta times, I'm going to factor out the rho. There's two rows, so I get a rho squared. And then I have, notice I get like the cosh phi d psi, that gives me cosh squared. And then I get this wedge that, which gives me a sinh squared, but it's got d psi wedge dt rather than t wedge d psi. So that gives me a net of t. dt wedge d psi. So my point is, if you look at all this, I've not written all the details out, but I can see from this that I'm going to have rho to the power 4 sine phi times t is my Jacobian. And like a 5x5 determinant, I think it's worse. I don't know. I mean, if you know property determinants, we can always go back and forth, which is better, but do you want me to do what I did yesterday? It's easier, but no. All right, let me stop talking about wedge products. It's not